Hi, I'm Stella Bichebe, and during this talk, I will present how we can take advantage of Intel PML for hardware-assisted working set size estimation of virtual machines. Page modification logging is an Intel virtualization feature introduced in 2015 that allows the virtual machine monitor or hypervisor to track write accesses of guests. This is done by extending the process that happens when dirty bits are set for extended page table during page work. The introduction of PML required some specific changes in the virtual machine control structure and VM mix root and non-root operations. Secondary processor-based VM execution control 17 has been defined as enable PML. A new 64-bit VM execution control field has been defined called the PML address. A new 16-bit guest state field has been defined as PML index, and a new VM exit reason is defined called the page modification log full. In the following slide, we will have a better understanding of these fields. The use of PML typically begins by enabling it on the VM for which it will be used. To do so, the hypervisor allocates a region in memory for the page modification log and initializes the PML index. Once initialized, each write that sets dirty flag in the extended page table will trigger the login of the corresponding guest physical address by the processor in the page modification log. Whenever the PML log is full, the processor triggers a VM exit notifying the hypervisor that will flush the log, reset the index, and resume the VM execution. The processor will only start logging again once the PML index is reset. While the VM resumes its execution, the DOM0 or the hypervisor itself can start processing the logs according to the operation they want to perform. At the end, the hypervisor needs to disable PML to avoid any additional unnecessary VM exits. This process could be resumed using a state diagram. During the page work on TLB miss, if dirty bit is set for the extended page table, the processor logs the corresponding guest physical address and decrements the PML index if the log is not full, otherwise triggers a VM exit notifying the hypervisor that will handle it. We conduct the study of PML using the Zen hypervisor and its impact on three operations: live migration, checkpointing, and working set size estimation. We study the impact of PML on live migration from two sides: the performance of user applications and the duration of live migration. Note that when PML is not enabled, the technique used by Zen during the live migration is the present bit invalidation. We used an application that passes an array several times. At each iteration, it performs a read or write operation to a set of entries in the array. This is to model read or write intensive applications type. We vary the write intensity going from read-only to write-only applications. The results for performance are presented on this graph. We can observe that live migration anyway negatively impact the performance of user application, but this impact is slightly reduced when using PML for live migration, and the improvement is better for write intensive application because using PML avoids the page fault generated when using the traditional technique of present bit invalidation. The results for duration are presented on this graph. We can observe that using PML, the live migration time can be improved by up to 10%, specifically for read intensive application, because with read intensive application, as there are few write operations, there will be few log full even, and then fewer VM exit generated. We study the impact of PML for working set estimation in terms of performance degradation on applications. We used the benchmarks we tried and sort from the big data suite and the HPL link pack, which is a very wide intensive application that performs arithmetic computations. The algorithm is as follows. From the DOM0, we collect all the guest physical addresses that are retrieved by the hypervisor until there is no new addresses in the log. Afterward, we compute the total number of distant guest physical addresses that have been collected. Such a working set size estimation system based on the current version of PML will either overestimate or underestimate the working set, and due to VM exits, overheads on application can go up to 34%, specifically for very write intensive application. Based on the result of this study, we introduced page reference logging, an extension of PML in which all accesses to guest memory are logged, read and write accesses, and on log full event, the processor does no longer trigger VM exit but rather send an interrupt to a DOM0 CPU that will be responsible of handling the log full event. Note that in a cloud environment, CPU of the DOM0 belong to the cloud provider. Then it makes sense to use it for working set size estimation rather than impacting the user application, because this operation benefit to the cloud provider who wish to do overcommitment. A processor supporting PRL will function in two exclusive modes. The first mode will mimic the current PML functioning to be sure that PRL is still effective for live migration and checkpointing, and the second mode will focus on working set size estimation. As for PML, some changes in the VMCS may be required to support PRL. A new 16-bit hosted field called the log full handler CPU may indicate the index of the CPU to which an interrupt is sent when the PRL log is full. A new 8-bit hosted field called the log full vector will indicate the interrupt vector to be executed by the target CPU upon reception of a log full interrupt, and the actual secondary processor based VM execution control for PML could be redefined as PRL enabled, and the system software will have the charge to activate each mode when needed. The difference with the PML algorithm is that as when using PRL there are no more VM exit. Before sending an interrupt, the processor must first check that there are no pending interrupt related to log full event. We implemented a working set size estimation system that leverages PRL to estimate the working set using this formula, where epsilon is the memory footprint and could be determined using the following algorithm. Start a virtual machine with an initial amount of memory. Allocate 95% of this amount to the VM. If the VM crashes, then stop. Else, restart the algorithm until the VM crashes and get the memory footprint. The size of a page, which is 4 kilobytes in our environment, and the number of hot pages. The estimation of the number of hot pages works iteratively. We define the minimal number of times a guest physical address must be logged for the page to be considered as hot. At each iteration, we compute the number of distant guest physical addresses that have been logged more than 2 times until this number becomes constant, which means that the VM has already referenced all the pages belonging to its current working set. We implemented PRL under Gem5 that we extended to simulate a virtualized environment. We implemented the extended page table support, which is needed for PML and PRL mechanisms. We implemented the working set size estimation using the simulator and a real virtualized environment. To do so, we run the application under the simulator and collect the guest physical addresses logged, including timestamp. After this, the traces are replayed inside the DOM0 of a real virtualized environment where the working set size estimation system run. A DOM0 CPU is dedicated to the estimation, while the other DOM0 CPUs replay the traces. Each time that a process replayed n traces, where n is the size of the PML log, it sends a signal to the process estimating the working set, thus mimicking the functioning of a real machine equipped with PML. To evaluate our implementations, we use the synthetic application for which the working set is known in advance. We use 3 variants of this application by varying the set of read and write operations. We also used a macro benchmark HPLN parsec. This graph presents the results for HPL and the synthetic application, and we can observe that PRL is always accurate with an error of 1 megabyte. These are the results for parsec applications. I present here the result for 3 of them: Fairhead, FaceSim, and X264, and we can observe that PRL is always accurate. This table presents the estimation of the number of guest physical addresses that are lost on logful event when using PRL mechanism. Remember that for PRL there are no more VM exit on logful event, so one may argue that some addresses belonging to the working set will be lost. Anyway, if an address is part of the working set, it will be seen very often, so losing one during a logful event does not compromise the estimation, as the address will be seen in the next iteration, as this result can prove it. We also evaluated the overhead of PRL on the VM and the DOM0, which is now responsible for the handling of logful event. As we don't have a machine equipped with PRL, we estimate that the overhead of PRL will be that of PML for read-only application. Indeed, the internal circuitry of PRL will be somewhat that of PML, except that there are no VM exit. So, for read-only application where there are almost no write operation, PML will function like PRL, so we can say that PRL will likely incur no overhead on the VM. We use the emulated environment to estimate the CPU consumption of the working set estimation system. We use the write-only application as the worst case. This graph presents the result for a single vCPU VM. We can observe that the CPU consumption increases until the working set is discovered. However, we can see that the CPU is most of the time idle, waiting for a logful event. In average, the CPU consumption is less than 1.5%. We repeated the experiment by varying the number of VMs, and we observed that the CPU consumption increases linearly with the number of VM. In conclusion, we have presented PML, which stands for Page Modification Logging, an Intel virtualization that allows the hypervisor to efficiently track write accesses of guests. We conducted a study and we have shown that PRL reduces by up to 10% the time of live migration, that PML slightly reduces the negative impact of live migration on application performance, and that a working set size estimation system based on PML can incur up to 34% of performance degradation. We have present PRL, that stands for page reference login, an extension of PML that we introduce, which is more accurate for working set estimation and still effective for live migration. We have shown that PRL incur less performance degradation than PML on user application. We have presented our implementation on Gem 5 and the results of our evaluations. Thank you.